Right, so I'm sure we will find out at the end that there was a better way. Anyway, so today I will, so first of all, let me thank the organizers for the invitation and for putting together this very nice workshop. Today I want to talk about something that I have been interested in recently, and this is about non-stabilizerness in many-body physics. Specifically, I will focus on some recent results that we obtained with my student, David Corbeny, and also Michael Gallants from the University of Maryland. And I also mentioned some previous work that we did on the subject. So I see there is a quite diverse audience, so I will start with a quite naive introduction to the concept of non-stabilizerness, which is something that comes from the quantum information community. And I will spend some time to motivate why this could also be interesting from many-body physics, and a bit of the recent context in which people from many-body physics actually started to do things on this front. And so in this spirit, let me start with really some very basic preliminaries. Some of the things that I will say have been already touched upon in the previous talk, but so let's start from here. So I want to consider now the standard setting for quantum computation, where we have some circuit that is depicted here. And in this picture, I have some initial state and have some time going from left to right. And for many-body physicists, the way that we can think of these diagrams are physical evolution, so sort of a quench where we initialize the system in some trivial state, and then we let it evolve according to some unitary dynamics. And basically, every time we have a 1-qubit gate or 2-qubit gates, this corresponds to, say, 1 or 2 body interactions. And we can really see, let's say, the output as a physical wave function on a proper quantum device. Of course, it's well known that in the setting, there is a way to, if you have a finite system, to produce all possible unitary evolutions on your system. And it's enough to choose your 1 or 2 body interactions from a finite gate set. The most common one is given here. So you have only a single 2-body interaction term, which is this C0, and then you have single body or single qubit operations. And so the main actor of this talk is the Clifford group, which is a subset of all the possible evolutions you can have in your circuit, which is defined as the one which is generated by forgetting about this T gate and only using evolutions which are made up of these, let's say, elementary pieces. So this defines a family of states, of evolutions and of states, which is, let's say, very special. And for many-body physicists, there is a natural analogy, which is the one of free fermionic Gaussian states or free fermionic states. So if you take any evolution, you can restrict to a class of states which has some special properties. This is the class of free fermionic state, where you basically restrict the type of 2-type interactions to be something that you can map to free fermions, say via Jordan-Wigner transformation. And here there is something similar. If you restrict the type of interactions between the qubits, you end up with a very special evolution and very special states. Specifically, the type of states that you can obtain by evolving the trivial state with this Clifford circuits is called the stabilizer states. And this is the type of family of states that I will focus on in this talk. There is an equivalent way of defining stabilizer state. It is not obvious that this is equivalent, but it is. And we can define a stabilizer state psi to be any many-body state which is stabilized, so that it's the common eigenstate of a commuting set of Pauli operators Pj, which are just strings of Pauli matrices. The simplest example of a non-trivial stabilizer state is the G at Z state, the scat state. You have n Paulis that stabilize it, so the first one is just the product of sigma x's, because this flips into 1 and this into 0, and vice versa. And then all the neighbors sigma zz that still stabilize their state. Again, so these are a family of states which is non-trivial. You can have entangled states, but they have very special properties. And for these class of states, one of the special properties is that we will use is that they have a flat entanglement spectrum. Namely, all the Reynolds entropies coincide. I will come back to this later. In fact, the entanglement entropies are quantized. This state, the cut state, if you compute the bipartite entanglement entropy at any cut, In base 2, the entanglement is just 1, and this is true for all the stabilizer states. Again, the analogy for many-body physicists is think of fermionic, free fermionic states that are special family of states with special properties, and here you have the same. So the Clifford, the stabilizer states play a very prominent role in quantum information and quantum computation theory, and really there are many reasons why these are interesting. But I want to focus on 2 that are relevant for us, and I think that these are the reasons why studying stabilizerness in many-body physics makes sense. The first one is that these circuits and state can be simulated efficiently on a classical computer, and in fact, it's very easy to simulate a Clifford circuit. Again, in the same way as it's very easy to simulate a Ising model that can be mapped to free fermions on your classical computer. So this is something that with Mathematica you can do very efficiently, up to hundreds of qubits. And then the second, let's say, parallel thing is that Clifford operations are very special properties that make it possible to devise efficient schemes for fault-tolerant implementation. Fault tolerance is something that is different from quantum error correction, and it's what allows you to implement gates and have a controlled quantum computation, even if the gates have errors themselves. And it's well known that if you have Clifford gates, this you can do, at least in principle, fault tolerant. So there is a strategy there which is efficient. And so you have this duality that on the one hand, you're happy to have on your experiment quantum gates because you can implement them fault tolerantly. On the other hand, you're not happy if you're in your experiment, you only have Clifford gates, because at that point, what are you doing? You could just put the circuit on Mathematica and have better results for larger system sizes. Okay, so, and then some other reasons, as this is, of course, all the stabilizer codes that were introduced previously are stabilizer codes, so they have a very prominent role in quantum error correction theory. Okay, but what if Clifford gate is all we can do? So the good news is that we can still achieve quantum computation. So, of course, if you only have Clifford gates, because you can implement them classically efficiently, they will not allow you to do universal quantum computation. But the good news is that if you supplement a Clifford circuit with some special state, then you can have something which is a universal quantum computer. And the minimal object that you need are states of this form. This is a mixed state, which, it's a pure state where whose density matrix look like this. And there is a known protocol that only makes use of Clifford operations that if you input a generic state and sufficiently many copies of the single state spits out as an output the application of this T state to your psi. So because the T state was the only thing missing from the Clifford group, this is enough then to implement universal quantum computation. And this is a very famous paper by 2005, which is also responsible for introducing the word magic, which is another way to denote non-stabilizerness. So let me take a step back. So these states that we called rho T before, they're not just special because they allow you to, let's say, complement universal quantum circuit with universal computations, but they're also special because, I mean, suppose that in an experiment you don't have exactly this, but has something that has a finite fidelity with it. Then Ravi and Kitaev proved that not only these allow you to do universal computation, but approximate versions of this state can be turned into, let's say, exact states with Clifford operations. So again, suppose that you have like a near-term quantum device where you can implement Clifford operations fault tolerantly, and then you can sort of approximately prepare the state rho T. Then you can use this protocol to have a fully functioning fault-tolerant quantum computing. What you do is you first prepare n plus m copies of this approximate state. You run this so-called distillation protocol that produces clean copies of rho T, and then you use them to inject your Clifford computer to then produce a universal quantum computer. And because of these dual properties of rho T that both makes your computation universal and can be distilled, Brevy and Kitaev call these states magical, and this is why the notion of non-stabilizerness, so not being a stabilizer state, is also called magic. In fact, I think this is only one of the two reasons why the property of not being a stabilizer is also called magic, and this is best summarized in this quote, this footnote from this very influential paper. And again, one of the two reasons is that these states have these apparently magical properties, but I think that the second reason is that the word magic lends itself to very nice and very easy puns. So, for instance, this is how this footnote is ended in this paper. But I think it's a bit, I mean, I don't like the word magic, so I will not use it in this talk. But so let's summarize. Non-stabilizerness is a property of quantum states which quantifies how much magic states, so how many of these rho t's you can distill from your wave function. This is still a vague concept, but it can be made fully precise within a quantum information theoretic resource theory. And it is experimentally accessible, so there are now papers where they extract this magic from experiments. I will not get into the details of this, but here the analogy is with quantum entanglement. So the best way that we have to define quantum entanglement is via resource theory. And what you do there is you have a bipartition and you define, let's say, operations that do not increase this entanglement, which are the local operation. And then there is a way to quantify entanglement based on these local operations. So in this resource theory, you quantify entanglement by anything which is not increased by these operations. And here you do the same, but the free operations are the Clifford operations. Okay, so I will, again, skip all of this, but then just to start to put down equations, one, let's say, recent development which has been very fruitful has been the introduction of a computable measure of this non-stabilizerness. So let's look at this equation, and suppose you have a wave function, psi, for instance, a many-body wave function, which lives on a n-qubit Hilbert space. Then you can, given this wave function, you can compute a number, and the number is obtained by computing the sum over Pn, and this is the sum over all possible Pauli strings of this form. You compute the expectation value, you square, you multiply to the n, you sum, and then you get a number. Exactly. Yeah, this is exactly it. And okay, so this is a number, was initially introduced as something that had some nice properties, but over the last 2 years, we have really understood that this is a good quantity because it's in some regime, it's really a monotone, so it's good also from the quantum information point of view. Specifically, so this has some immediate property. So this quantity is 0 if and only if your state psi is a stabilizer state. It's also additive. And then much less trivial is to show that this is actually a monotone so that it cannot increase if you apply arbitrary Clifford operations. This was first discussed in my paper with Tobias, and then the monotonicity for n equal larger than 2 was finally proven in the subsequent work. All right, so also, let me comment that this is seemingly something, so I said that this is computable. It means that there is no minimization over an ugly space. So at least it's something that for small system sizes we compute on Mathematica. There seemingly is still an exponentially large sum, but again, we'll come back to this. Some recent work have shown how to evaluate this explicitly, at least in some families of states, including matrix product states. Right, so a stabilizer operation is anything that is any quantum channel that is made up of a few ingredients. One is stabilizer, Clifford unitaries. One is projective measurements, and then any adaptive operation based on projective measurements. And Pauli measurements. Yeah, so you fix a base and then you have to create this. And from the classical point of view, any such channel is efficiently simulatable on a classical computer. Okay, so this is sort of completes the quantum information side of the story. And now we have the question, why should we care as many-body physicists? So first of all, the reason why many people got interested from the many-body community, I think it's a bit underwhelming, and it is just because finally there was a quantity that people could compute. Before that, so before 2022, this was not there, and the only way in which you could quantify this quantity is minimizing over something which is too ugly to be written down in one line. Yeah, I mean, well, I mean, not uncomputable, so you have a quantum definite program, so it's exponentially costly in a very bad way. Easier, yes, exactly. And also, in some cases, like for MPSs, this turns out to be polynomial okay, so then, okay, we have this quantity we can compute, but then, in fact, I think there are two strong reasons why many-body physicists should be interested in this quantity. And the first natural, let's say, reason is about quantum simulation. So you know that we have now these devices which are not good enough for quantum computation yet, and so one of the best options or most reasonable way in which we can think we can use them in the near future is quantum simulation. So you have some wave function, so maybe some lovely wave function or something that you know explicitly. You hope to prepare it as the output of a quantum circuit and then measure that. So the idea is that if you have a way to quickly extract whether a wave function, like the lovely wave function, has non-stabilizerness or not, then this tells you whether you should suffer or not to implement it on your device using many qubits, many gates which are not, let's say, Clifford. So this is one already immediate motivation. Basically, this has to do with experiments. Then there is another one which is about, I mean, it's more theoretical, and this is about computational complexity in some sense. If I give you some wave function and I can guarantee that it has low non-stabilizerness, then the expectation is that this wave function is something we can easily simulate classically, so it's not really complex. This is a bit vague of a concept, but it has been made precise. And then there is a more speculative direction, which is what a lot of people started to look into, which is, okay, but what if this quantity has also something to teach us about maybe structure of wave functions in many-body physics, again, paralleling the story of entanglement, okay? This is a Rényi entropy of something. So I will let ChatGPT answer for me. So this is, yeah. Okay, so I mean, I will not talk about this quantity anymore in the rest of the talk, but basically, psi p psi, as you vary p, is a probability distribution with generally 4 to the n entries. And this is a Rényi entropy of this classical probability distribution. Okay. Sorry, but now, okay, and then there is this more speculative direction here. I just put some work. So there is, I think, this one where Mari Carmen is involved, and probably some people in the audience have worked on. But these works pertain to try to see whether there is something interesting from the many perspective when we really aren't. We put the many-body glasses on. Now, okay, so at this point is a time to address the elephant in the room. And the elephant in the room is that this quantity is very strongly basis dependent. So, I mean, one of the questions at the beginning, after this quantity was introduced, people started to compute it, of course, in the ground state of the ESI model, maybe look at what happens to the phase transition. And they found that had some nice spikes at criticality. But there is something, I mean, already strange, because this is strongly basis dependent. So you would expect that this is strongly UV dependent. So how can this tell you something about phase transitions and divergence of correlation lengths? Indeed, this is where we, in this work with Tobias, we first pointed out that this quantity can be computed efficiently in MPSs, and we revisited the computation in the ESI model. And here I plot this quantity as a function of n. So it's the intensive value of this quantity. This quantity in general is extensive in the system size, so this is just a leading behavior. And here, let's focus on the first plot. Here you see different curves. So you see the blue one, which has a peak at criticality. And this was the first calculation from an earlier work where they show, well, this is amusing because it has a peak at criticality. But now I also put different colors, and the different colors are just obtained by locally rotating the basis. So you see that locally rotating the basis, you get that maybe this non-stabilizer can be maximum, or can be a minimum, or can be something in between. So if you only look at the leading behavior, it's not true that criticality is associated with a peak in this quantity, as you would expect. This is just a zoom in for some rotation. But now already what we observe is that maybe there is something interested if you try to define a quantity which is independent from the UV contribution. So here we try to minimize over local change of basis, so strictly local changes of basis. And what we found is that indeed there is some spike. So the orange one is for 120. You can see that there is a spike at criticality. So already here, 120, this is done with efficient MPS methods. And this tells you that this quantity is much more computable than was before. And then people like Mari Carmen and others improved our initial suggestion. It is not, but this is a finite size. We did some scaling. But also here, the point is that we only minimize about strictly local operations. And a more physically, let's say, sensible thing to do, and this is what I will discuss next, is to minimize over finite dead circuits somehow. Indeed.
And it seems as
yeah.
The orange curve.
Indeed. But this is, I mean, sorry?
Is there some information?
I would argue that this is exactly why this quantity could be interesting from the quantum simulation perspective. So imagine you wanna put on your computer the quantum model. I care about long-range properties, so I don't care about the basis. So the first thing to do is I look at the basis which minimize it, and that is the basis in which I will implement the ESI model on my quantum computer. But the meaning, yeah, I don't know. This is, I guess, yes. But let me continue because this is just a part of the story. Okay. So the continuation of the story is that this was just an initial trial, but indeed we only minimize over strictly local pointwise operations, but this is not the most general thing to do or the most sensible thing to do. And in any case, so these many-body perspective motivates the introduction of a quantity, which is related maybe to stabilizerness, but is basis independent. And so colloquially, you can think of saying, okay, we can say that a state has long-range non-stabilizerness if there is no local transformation that maps the state to a stabilizer, where local now I will introduce in a second, but it's more general than just pointwise rotation. I should say that this concept appeared, I believe, first in the paper by Swingel's group in the context of CFT. It wasn't really made fully precise, but all the ideas were there. And also in the context of symmetry-protected topological order, there was a version of this story in this paper by Tyler and others. But this was essentially everything that there was before our paper about this type of non-stabilizerness. And a lot of questions were unexplored, even in the simplest setting. Even the definition, these use different definitions, so there was not a clear, let's say, setting. Okay, so now this is the stage, and let me come to then what we did and the punchline. So what we did in this work, we first gave a precise definition of this quantity, long-range non-stabilizerness in the many-body setting. And we give a simple argument for why this is a very generic property of many-body states, in the same way as long-range entanglement is a generic property. Just because if you pick a state in the Hilbert space at random, it will have a volume law entanglement, which you cannot trivialize with a finite circuit. And then, let's say, specify then the story to to ground state of gap Hamiltonian, so we get closer to previous talk by Kurt. Then we have a partial classification of long-range non-stabilizerness in one-dimensional ground states of local Hamiltonian, and specifically we give results in the context of matrix product states. I should also mention that after we posted on the archive, these two papers appear. So the first one is similar in spirit, but focuses on a perspective of quantum error correction. So they give complementary results, but it's quite a different story. And then very recently also there was a paper by Natalie, she's a computer scientist, and it was yet another perspective, but some of the ideas that we use were also appeared here. Okay, so this is, again, to point to the fact that this is a very interdisciplinary problem, and I think it could be interesting for different communities. Okay, so now the plan for the next 10 minutes is just to basically walk you through our argument and what we did, and then mention some open directions. Okay, so first of all, I mentioned local operations, so local changes of basis. Again, this is a recurrent theme from previous talk. So first of all, I want to define what it means for a physics perspective to have a local change of basis. And this is any operation that you can implement by a shallow local quantum circuit. So shallow circuits are graphically depicted here. This is in one dimension. What you need is you need a connectivity, and then you need gates respecting that connectivity. And if you do this, then you see that any point has a clear backward light cone. And this mimics really what happens in local Hamiltonian dynamics. When you have the start of states that are prepared in this way, then they naturally satisfy a cluster decomposition as written here. And so this is, let's say, just a definition, but shallow quantum circle gives you a very practical way to define and understand the topological phases and long-range entanglement. And again, this is work by a group of Gang and others. Okay, so let me first mention on something that was already discussed by Kurt, and this is about how quantum circuit can be used to define actually topological phases. So suppose you have two ground states of some gapped local Hamiltonian, then the traditional way of thinking about topological order is that the two states are in the same phase if I can deform smoothly the Hamiltonian without closing the gap and under some assumption such that I go from state 1 to state 2. And then in 2004, Hastings showed that this is basically equivalent to saying that the two states are related by this local transformation. The idea is that this shallow circuit cannot generate a long-range entanglement, and so this corresponds to smooth deformation of the state that are locally from the physical point of view. Okay, so so basically you can take this now a definition of topological order, but in particular also for long-range entanglement. And this is an old idea. For example, here there is a very famous paper by B. Hastings and Verstraete where they talk about this and the connections to local Hamiltonian dynamics. And again, a very simple example of this is the G at Z state. And the way in which you realize that this is not a short-range entangled state, according to this definition, is that if you compute the correlation, the expectation value of Z1 Zn over 2, so two parallel images is one at the beginning and 1/2 of a one-dimensional system, this will not factorize. And this is enough to prove that you need a circuit which has a depth which is at least linear in the system side. Okay, so this is interesting also because it tells us that, so remember that the GZ is a stabilizer state. So it tells us that stabilizer state can have long-range entanglement. So whatever long-range non-stabilizerness is different from long-range entanglement. So here, let me give the definition that we give, which is epsilon and delta definition, which I will now explain. Okay, so we imagine we have a sequences of state psi n, because we want the system size to scale. And then we say that a state psi n has long-range non-stabilizerness short-range non-stabilizerness if it can be mapped to a stabilizer state via finite circuit. Okay, so here, this is a fidelity between your target state and Sn, which is the stabilizer state. And then you want this to be smaller than some epsilon n. And now for technical reason, ideally you could define this to be 0. But for technical reason, we still want to allow for some error, because otherwise the definition is too strict. So we allow for some error, but then we can let the error go to 0 in the system size with an arbitrarily mild way. Okay, and so this is the definition that we give, and according to this definition, then it's very easy to see that this is a stronger definition than long-range entanglement. For example, this is a simple table. SRE means short-range entanglement, long-range entanglement, short-range non-stabilizerness, and long-range non-stabilizerness. And there are trivial examples for these two cases. The product state is both Clifford and non-entangled. The G at Z state now is Clifford, so not short-range non-stabilizerness, but long-range entangled. And by sort of definition, because the state 0, 0, 0 is Clifford, it's not possible to have long-range non-stabilizerness in the absence of long-range entanglement. So the only non-trivial bit is, okay, what are the states here? And this is what we give sufficient conditions for in our theory, in our paper. Okay, so we give two results. So the first one is a typicality argument for why this, with this definition, long-range non-stabilizerness is typical. So sadly, or luckily, most of the states in a many-body setting are hard from the Clifford point of view, and this is sort of we expect, because we expect that most of the states in the quantum many-body setting are not simmutable. But the argument is extremely simple. So let me first define three numbers. So the first one is the number of states that we have in a many-body Hilbert space that you can distinguish up to some epsilon error. Okay, so this is the number of epsilon bolts. Then you define the number of stabilizer states, and this is a discrete number. Because due to the special property of the Clifford circuits for finite n, this is a finite number of elements. And then we also define the number of local circuits of depth d that you can apply up to some error epsilon. And it's very easy or already known how to estimate these numbers. And the important bit is that there is a mismatch in scaling. So the number of states in a Hilbert space scales doubly exponentially with the system size, whereas the number of stabilizer states grows much slower. And also, it's easy to estimate the number of local circuits. Basically, you count the number of space-time position for a gate, which is n times d, because it's in one dimension, for example, is n times the dimension. This is just a rectangular. And if you allow for a finite number of gate set on your position, then this is going to be just the exponential of n times dn. And this is just a logarithmic overhead due to taking into account errors. So if you cross if you take into account all the details, then you arrive at an estimate that the number of epsilon bolts, so of states, is exponentially larger than the number of stabilizer states, which is just the number of input circuits, and S times the number of circuits. Okay, so this is a very simple argument, which again we expected. Now the question which is more interesting is, okay, but what happens if we now specialize the discussion to ground states? And here is also where the story, for example, about long-range entanglement becomes interesting. Because also for entanglement, I mean, if you pick randomly a state in the Hilbert space, it has volume law entanglement and you cannot trivialize it. But then if you look at ground state, then you have a way of classifying states and then defining phases of matter. We would like to try to see whether something like this we can do also when we discuss about stabilizerness, non-stabilizerness. Okay, so of course we focus on one-dimensional system because it's the easiest, and not only that, but we focus on a toy model for ground states of gapped Hamiltonians, which is that of translation-invariant matrix product states. And I mean, this just a few words on this. This is an ansatz wave function, which has been extremely popular in the past 20 years. And in particular, there are a lot of proofs showing that these are very good approximations for ground states of Hamiltonians. And specifically in the case of translation-invariant states, there are a lot of rigorous results, most of which derived by Norbert, Ignacio, David Perez-Garcia, and Frank Verstraeten. And one of the nicest results that they derived is the possibility to derive a renormalization-group flow. So basically, once you accept that ground states are defined by MPSs, then you have a way to rigorously define a RG flow. And this RG flow is a way to start from a matrix product state and look at what is the corresponding fixed point if we look at real space RG. The fixed point is defined by some technical condition, and as you would expect, the states that satisfy this condition are the fixed points, and their correlation length can be either 0 or infinite, as for any fixed point theory. And an example, again, is the GZ state. This would correspond to a state with infinite correlation length. And also another thing which could be useful is to keep in mind that this RG flow fixed points have been completely, again, classified by Norbert and the others, and they are always associated with a minimal degeneracy of the parent Hamiltonian. So for example, for the GZ state, this you need a Hamiltonian, which is at least degeneracy 2, and this would correspond to 2 symmetry broken, let's say, ground states. Okay, so, and then another piece of the puzzle that we need is something which is more recent. So this is a work, okay, so the piece of the puzzle that we need is that it has been shown recently that if you start from a translation-invariant matrix product state, then there is a way to map it to the corresponding fixed point by a shallow quantum circuit with a depth which is only logarithmic in the system size. And this has been done in the work by Daniel Maltz, Yorgos in the audience, Wei and Sirac, and building upon our previous work, again, with Yorgos and Ignacio. And so now this is useful because it tells us that if we want to classify long-range nonstabilizerness in MPSs, then it's enough to do it for, let's say, fixed points of matrix product states. And finally, we now get somewhere because Norbert and the others have classified for us these fixed points, and they have shown that they have an extremely simple form. The simple form is written here, so up to local isometries, they basically correspond to sum of a finite number of terms of product states that are locally orthogonal to one another. Okay, so I'm skipping some details here, but this is mostly accurate. And let me now, in order not to be too technical, let me specify the story to something very, very simple. Okay, so now we can forget about MPSs and all this stuff, and let's just focus on the state. So this happens to be a fixed point, MPS. It has infinite correlation length, but if you play around with parameter alpha and beta, you obtain a family of states. And now I ask you, for which values of alpha and beta does this have a long-range nonstabilizerness? Okay, the first trivial observation is that if you take both of them to be 1 over square root of 2, you have the GZ state, so 0 nonstabilizerness. Another simple observation is that if I take one of them to be a phase, like e to the I phi here, then this has short-range nonstabilizerness because I can just apply a unitary on the single first qubit. This is a trivial depth 1 circuit, and I can map it to the GZ state. So again, short-range nonstabilizerness. But then the question, okay, what happens if now I take some arbitrary alpha? This is what we can show that in this case, for any alpha different from 1/2, this has long-range nonstabilizerness. And this is implied by our theorem, which tells you that if you have this fixed point, then this has long-range nonstabilizerness if, a sufficient condition is that the classical Shannon entropy of the coefficients alpha j squared is not an integer. Sure, but yeah, exactly. So, but then what we prove is that you will never find a finite quantum circuit that gets you arbitrarily close to a stability state. Yeah, indeed. Okay, so I mean, in practice, this means that if you want to prepare the state, you will need to either, so any type of let's say. I mean, here, this is not a stability state, so you expected that you should use something non-local. But here, the point is that this non-local thing has to be a non-stabilizer state. Okay, so this is the theorem that we prove, and so now let me just give the idea because it's very intuitive in the simple setting. And the idea of our proof is to look at how mutual information behaves under finite depth circuits. Okay, so we exploit, okay, so first of all, consider this picture and only focus on the top. We have now 3 regions, A, B, and then C, which is the union of these two. And we can study the mutual information between distant intervals, which is the standard definition. And then the proof is based on 3 ingredients. The first one is that based on a careful analysis of the background light cones, we can prove that for sufficiently large A and B, for fixed points, the mutual information is invariant under finite depth circuits. And so in particular, for the states that we consider here, for instance, so the mutual information of this is simple to compute, it's trivial. And we prove that it's not changed by the quantum circuit. So we show that, this is always equal to the Shannon entropy. Second piece of information is something that is well known, in that the mutual information between stabilizer states is always quantized. And so, and finally, we have a continuity condition of the mutual information, which stems from the so-called finiteness inequality for the entropy, which means that this is stable under small errors. And so if you put the three ingredients together, you realize that if your mutual information of the initial state is not an integer, is not quantized, then this is, I would say, a topological indicator that you have long-range non-stabilizers. Okay, and just a comment that this is this continuity with respect to regions is what differentiate our work from the quantum error perspective that came after in the subsequent works. Okay, so now I'm finished. I will skip the open technical questions. So the outlook. I think that there are many open directions. I would say that the most obvious direction is to extend this to maybe critical phases. So this was about ground state, but what happens if we try to look at, say, mirrors that represent critical ground states, or maybe higher dimensions? And also I want to mention that some of the directions we're currently exploring is to use now this way of looking at non-stabilizerness to detect, to extend previous theorem about the possibility to implement encoded universal quantum computation beyond the stabilizer codes. With this, I'm finished, and I thank you for your attention.